Hey everybody, we are going to talk about evaluating definite integrals here. So looking at methods for calculating what is the value of a definite integral. So first we need to be clear on this idea of an antiderivative. Basically it's the antiderivative of some function f is any function capital F that whose derivative is f. So if you can figure out what that function is, then you found the antiderivative. So you kind of have to work backwards using all the rules of derivatives that you have, that you've learned. And if you are evaluating f of x dx, this is what you call an indefinite integral. So you can say that the indefinite integral of f is of f of x dx is capital F of x. Okay, so that's the idea. We're going to be using antiderivatives to do this. Here's a table of some of the antiderivatives that come from what we've seen. Now you see that in all of these you have this plus c added to the end, and the reason is because when you take the derivative, any constant is going to not appear in the derivative, right? So any value could be put in for c, and for example, for the function x to the nth, right? So for example, the integral of x squared dx would be x to the third over 3 plus some constant. So because when you take the derivative of x to the third over 3 plus c, the power rule says that 3 comes down as a coefficient. You'll have x squared. The 3 coefficient and divided by 3, those cancel, and then you'd have x squared only. The derivative of c is 0, so any value c would just be gone. So anyway, I just want to show you all of the ones we've learned. You can turn each of these into a derivative rule. The derivative of a sine is a cosine. The derivative of a negative cosine is a positive sine. The derivative of e to the x is e to the x, and so forth. So here's a little table of some of the antiderivatives that we'll be using. So so now we have the theorem that tells us how you evaluate a definite integral. So if you have a continuous function, little f, on the interval from a to b, the definite integral from a to b of f of x dx is capital F, its antiderivative, evaluated at b, minus capital F evaluated at a. So this is what you have to do. Find the antiderivative and evaluate it at the two endpoints. Take this example. We have f of x is e to the x, and we already know that capital F, its antiderivative, is also e to the x because the derivative of e to the x is e to the x. So capital F of x, that's the antiderivative of e to the x. Well, this tells us that we should just evaluate f at 3 minus f at 1. So that's e to the third minus e to the first. So it's e to the third minus e. That would be the evaluated definite integral that we're given right here. Take another example. Now finding a general indefinite integral for this function. I'm going to use some rules of integrals. For example, I can pull the 10 out front. What I'm going to do, actually, I'm going to do it a couple of different steps. First thing, I'm going to split this into the difference of two integrals. So we have 10x to the fourth dx minus the integral of 2 secant squared x dx. Okay, and now I'm going to actually take the 10 out front, and I'm going to take the 2 out front of this other integral, secant squared x dx. Now using the indefinite integral rules, we had the integral of x to the n dx is going to be x to the n plus 1 over n plus 1 plus any constant c. I'm going to actually add the c on at the very end of this thing. So this first integral would be x to the 5th over 5, and the 10 is going to be just hanging around there. Now what's the integral of secant squared? The integral of secant squared x dx, you can think, well, what function its derivative is secant squared, and that's, of course, the tangent of x plus c for a general indefinite integral. So it's going to be tangent of x. And I'm going to just put the plus c on the end now, because this any constant value would be gone when you take the derivative. So actually this 10 over 5 can be written as 2x to the 5th minus 2 tangent of x plus c, and we have our indefinite integral. Here's another one where we want to use the power rule, right? So we're going to evaluate this. Now the rule said that the integral of x to the 3rd would be x to the 4th divided by 4 minus 6 times the integral of x would be x squared over 2. So the way we write this when we take the definite integral, we put this vertical bar and we put the two bounds. Which you could also sometimes people put this in like a bracketed parentheses and just show that we're going to be evaluating at the two bounds. But this is pretty typical, putting this vertical line on the right-hand side with the two bounds. And now we're going to go and actually, let's see, I can clean this up a teeny bit, put that as 3x squared. So we're going to plug in the 3. We'll have 3 to the 4th over 4 minus 3 times 3 squared over 3 squared, yeah. This is f of 3 minus, if we plug in 0, we're going to get 0 to the 4th over 4 minus 3 times 0 to the 4th. Well, this is f of 0. So in the end, that's what we have. We have 3 to the 4th, which is an 81. 81 over 4 minus 27, which I'm just going to leave just like that. I'm fine with that. So take another one. Now I'm going to, here I'm going to be a little bit more explicit. I'm going to try to find f of x. I'm going to find a antiderivative. No, I'm not looking for the general antiderivative, just a antiderivative. So where this is my f, for the first term, we're going to be able to have x to the 4th over 4 times that 2. So this is my antiderivative of x to the 3rd, x to the 4th over 4, minus 6x squared over 2. Now, what's the derivative of 1 over, the integral of 1 over x squared plus 1 dx? You remember, this is the arc tangent of x. Put the plus c there. But the derivative of arc tangent is 1 over x squared plus 1. So I'm going to have 3 arctan of x. That 3, and then I'm not going to put the plus c because I don't need to use the general antiderivative. I'm just going to use a antiderivative. I'm not so. So then what I'm going to do is evaluate f of 2 minus f of 0. All right, so this is going to be, f of 2 is going to be 2 times 2 to the 4th over 4 minus, that's 6 over 2 is 3. 3 times 2 squared plus 3 arc tan of 2. Now I'm going to subtract f of 0, which is going to be 2 times 0 to the 4th over 4, of course that's 0, minus 3 times 0 squared, which is of course 0, and then 3 arctan of 0. The tangent is 0. The tangent of x equals 0 if the sign is 0, if x is 0. So 0 has an arctangent of 0, so that's going to be 0 as well. So the arctangent of 0 is 0, so this whole thing here is just equal to 0. So then this simplifies a little bit. We're going to have 2 to the 4th times 2, that's 32 over 4, that's going to be 4, minus 4 times 3 is 12, plus 3 arctangent of 2. The arctangent of 2 isn't anything special. So I'll just write this as negative 8 plus 3 arctangent of 2. That's good enough. So here we have another one. Now this is a funny one. It looks like it's going to be really awful, but the key thing here is to actually split this up into a sum of 3 fractions. So this, I'm going to have the integral from 1 to 9 of 2t squared over t squared plus t squared square root of t over t squared minus 1 over t squared dt. Right? So now each of these can be simplified a little bit. It's the integral from 1 to 9 of 2 plus, I'll write this as t to the 1/2. It's going to be easier to work with if this is a fractional exponent, minus t to the negative 2. And so I'll use the notation I used before where I'm going to write these. So 2t, the antiderivative 2 is just 2t. The antiderivative of t to the 1/2 is going to be t to the 3/2, and then I'm going to have a 2/3 out front. So 1 over that exponent. So the reciprocal of the exponent. Minus t, I'm going to be adding 1, so it's going to be minus 1, and then it's going to be a minus 1 out front. 1 over minus 1. So it's actually a positive 1. From 1 to 9, clean up a tad. I guess the only thing I really want to clean up is this last term. And I'll write it as 1 over t now, from 1 to 9. So I'm going to evaluate this thing at 9. So that's going to be 18 plus 2/3 t to the 3/2. That's the square root of 9, which is 3 cubed, which is going to be times, that's a 27, plus a 1 over 9. Okay, so that's this antiderivative evaluated at 9 minus what we get when we plug in a 1. So we're going to have a 2 plus a 2/3, and we'll have plus a 1. So here, this 2/3 of 27. That's 2 times 9. That's another 18. So we're going to have 36 plus a 9th. And then this is minus all this. This is minus 3 minus 2/3, which, okay, so 36 minus 3 is going to be 33. And 1/9 minus 2/3. 2/3 is 6/9. So 1 minus 6 that's minus 5/9. That's good enough. I'll leave it like that. So here we have a theorem that applies to when you interpret the function as the rate of change. So the integral of the rate of change is the net change. So when you integrate the rate of change, you find the net change. So for example, if you're integrating a velocity, you're going to find a definite integral of velocity is going to be a difference. It's going to be the distance traveled. Okay. So here's and then there's other examples you can see if you have population growth, like the rate of growth is the changing rate of growth over time. If you integrate the rate of growth over time, what you're going to find is like the change in population over this period of time. So Here's an example. If a particle is moving along a line, its velocity is given by t squared minus t minus 6 in meters per second. We can find the displacement of the particle during the first, between time 1 and 4 by doing performing an integral, right? So for part A, the integral from time 1 to 4 of the velocity t squared minus t minus 6 is going to give us the displacement, the net difference in position. So this is going to be 1/2, so we have t to the third and a 1/3. We have minus 1/2 t squared minus 6t. And we're going to evaluate that from bounds 1 to 4. So this is going to be 1/3 times 4 to the third minus 1/2 times 4 squared minus 6 times 4 minus this thing evaluated when you plug in a 1, which is going to be a 1/3 minus a 1/2 minus a 6. Okay, just work that out and you get negative 9/2 meters. So what this means is the net change is it's gone backwards 5 or 4.5 meters. That's negative 4.5 meters, right? Now the distance traveled is going to be different if this thing wasn't going forward the entire time. Let's think, is the velocity ever 0? Let's see. Let's try to find when if the velocity of this thing is ever 0, which means it will change direction, right? T squared minus t minus 6. That's going to be t minus a 3 and t plus a 2. So at t equals 3, this this particle changes direction. So what we can do to find for B, to find the distance traveled, we have to find the position at the change in position at time 1 to time 3, and then from 3 to time 4. So that's what's going to matter for us. So we are going to take the integral from 1 to 3 of t squared minus t minus 6 dt, and actually just take the absolute value of that and add it to the total distance from time 3 to 4 of t squared minus t minus 6 dt. So take these two absolute values. So in fact, what we're going to be doing here is going to be the absolute value of 1/3 t to the third minus 1/2 t squared minus 6t going from 1 to 3 plus the absolute value of 1/3 t to the third minus 1/2 t squared minus 6t from 3 to 4. So add those two absolute values and you're going to get the net difference, or the total distance traveled. So this first one is going to be, let's see, 1/3 times 3 to the third minus 1/2 times 9 minus 18 minus the 1/3 minus a 1/2 minus a 6 plus this other part, which is going to be 1/3 what is that? 1/3 times 4 to the third minus 1/2 4 squared minus this 24, 6 times 4. And they do the difference between that and 1/3 3 cubed minus 1/2 times 3 squared minus 18. Okay, absolute value of that. I'm not going to bore you with all the details. You work this out. And you'll get 61/6, which comes to about 10.17 meters, roughly. So the total distance traveled as this thing started. This you could kind of see in time at what the point at time. If let's say the position of this thing over time t, and let's say the position. This thing started here at time at time 1. This thing was it was this thing would have moved something like this, a position. So we would have gone. This is like this. At this point, we would have gone some distance towards the negative, and then we turn around and come up a little bit. That if you add up those two distances traveled, just the vertical distance, then you would get 10.17 roughly. Now another way you can interpret this, if we have here this figure showing the power consumption in San Francisco during a day in September in megawatts. So this is over the course of every hour. What was the megawatt usage? So we want to find the total energy of the consumed in that day using kind of estimate it. And the way I would kind of do this is to I'm going to do this in just like blocks. So for example, I'm going to let's take I'll take this. Oh, what's a good estimate? It's probably this. That triangle. I'm going to do this in like little triangular blocks. And that looks like about, that's overestimating a tad, but that's okay. So I'm going to take this block. So, and let's see, from here to O, I'm trying to like just estimate a little, be kind of fair in how I estimate it. And I'm going to just take this as half a block high. Okay, take those down to there. I'm going to go straight across, and then let's see if I can go like that. So what do we have? First, I'm going to look at this area here, which comes to about, let's see, it's 24 hours, 24 times 4, that's 96. Oops. The height of each of these is 100, so that's actually 9600. And then we have a few that are let's do a couple more that are rectangular. Let's do this here, and then let's say this one here is going to be another rectangle, and those are going to be, fill in this one, this is going to be another rectangle, and just get all of these that are full rectangle. So just counting up all of these, if I go through and count up all of these rectangles, we got 5,400 roughly, and let's do the little triangular pieces. You can see here this works out to be let's see, those two together, and these they're about the same. All of them are, we've got another 100 here, another 100 there, another 100 here, another 100 here, another 100 here, all together on the top row. In let's put that, we have these bits in yellow, and we have also this little section in green. So we've got another 150 over here. That's the combine of those three half triangles, and then that's 6 across and then half wide, so that's about 300 altogether up there. So we've got 9,600, we've got 5,400, We've got they got 500 in the red. We've got 150, and we've got the 300. Okay, so altogether, my estimate is about 15,950 megawatt hours, just by roughly trying to estimate I'm sure that I was off by a little bit, just an estimate. I cut some corners, of course, but this is a rough estimate. That's fine. Okay, so there's our example of, our. Let's go back a second. Okay, so that's how we are. That's what we're going to do now for evaluating definite integrals. Here's where the challenge lies. Every function that you look at, you can find its derivative, but not every function has a clear antiderivative. And there's a lot of tricks that we may have to employ in order to find antiderivatives. So integrating is a tricky business, whereas derivatives are relatively straightforward. Well, we're going to be looking at a couple of tricks. Well, actually, one trick in particular, a simple substitution, in a couple more sections later. But the next course in calculus really goes through, spends a lot of time finding ways of doing integrals. All right, ta-ta for now.